Okay, so thank you everyone for joining us today. My name is Yakir, and we are going to talk about how we are counting unique users in real time. So I'm leading the R&D unit of a unit called Nielsen Marketing Cloud. I mainly focus on big data processing and machine learning solutions. And co-presenting with me today is Itai, who is the tech lead for our big data group. And he has been dealing with big data challenges for quite some time now. So what we are going to discuss today. So first of all, I'm going to present you the NMC, Nielsen Marketing Cloud. What are we doing? What is the business problem that we are trying to solve? I'm going to also present few possible solutions to the problems that we have. And then Itai gonna give you an overview of Druid, how we used it to solve these problems, and he also gonna share with you some guidelines and pitfalls. So Nielsen Marketing Cloud, for those of you who don't know, it is based on the acquisition of Excelate 4 years ago by Nielsen. We are essentially a data company, which means that we get a lot of data, a lot of device level data from various sources, online and offline sources. So for example, we have integrations with different publishers where they put our pixel on their site, and then every time that a device serves to their site, we get an event with everything that happened on this session. Later, we use all the data that we collect together with machine learning models in order to generate better insights. We build profile for each device, so we can understand that a specific device, for example, is being used by a male, and then we assign the attribute of male to this device. So our profile consists of the different attributes that we generate. All the data, the profile, and the attributes that we generated is being used by our clients for 2 use cases. The first use case is for them to get better business decisions. So they can use the data to understand the audiences, their audiences much better, and also get various reports about the campaigns that they are running and in general about their audiences. The second use case is around targeting. So we load all the data that we generate to different ad networks, of course based on the client demand, and then our clients can use the data and can use the ad networks to target specific audiences through the ad networks. Okay, so to give you a very high-level overview of our architecture, everything starts with the front-end layer, which collects all the data from the various sources. We are talking about more than 5 billion events every day. Actually, nowadays I think that we have 10 billion events every day. On this layer, we are running the different machine learning models that generate the attributes and build the profiles. Later, all the data is being sent through Kafka to our backend layer or big data layer. Here we have a set of various ETLs that are loading the data, reading the data from Kafka, running set of transformations, aggregations, and eventually we load everything to different data stores. So we use Druid, of course. We also have our own implementation of a data lake based on S3. We also use Snowflake, and we have many other technologies here. The third layer is our applications layer. This layer consists of the different applications that are being exposed to our clients. So our clients use these applications in order to get answers to the different questions that they raise. And of course, that for answering these questions, the applications are using the data that we prepared on the data stores on the previous level. Okay, so what are the business questions that we try to answer? Essentially, there are 2 types of questions that we try to answer. The first question is a uniqueness question. So let's say that we have a client who wants to run a campaign for young women who love steak. So he defined the attributes for his campaign. So in this case, it's going to be female in a specific age with a specific annual salary, also live in the United States. And we need to be able to give him the result in almost near real time of the number of unique devices that he can reach if he will run this campaign. So this is the first type of question. The second type of question is just a simple count question. So let's say that our client ran the campaign and his campaign got impressions, and now he wants to understand or to count the number of impressions to measure the effectiveness of his campaign. So we should be able to collect all the impressions and just do the simple counting. So to be more concrete, this is one of the screens from our system. And here you can see our client define an audience which is being used later for a campaign. So if you are going back to the previous example of a campaign for young women who love tech, so on the bottom part of the screen, you have the client can see the different attributes, and then he drags them to the upper part of the screen. And while doing so, you also define the relationship between the different attributes. So you can see that in this case, it's an and relation. So we are basically looking for all the devices in the intersection of these attributes, because we are looking for female in a specific age, in a specific region. And what we need to do is to calculate in real time the number of unique devices that we have that satisfy this formula for the last 30 days. And of course that we show just show the number here in the blue box. So at this talk, we're mainly going to focus on the count distinct problem, because this is the more challenging problem to solve, especially at scale. We can ignore simple counting for now. So if we try to generalize the questions that we try to answer, is basically we need to be able to find the number of unique devices that we have over some date range and with some set of attributes. And if we think about it, it's basically the count distinct problem with just a small twist of doing this for a combination of attributes. Okay, so we've been dealing with the count distinct problem for a few years now. Actually, I think it was 4 or 5. And historically, we used Elasticsearch for solving this problem. However, we had 2 problems with Elasticsearch. The first one was around indexing the data. So just in the ingestion process of 250 gigabytes of daily data took more than 10 hours to complete, which is a lot, especially as 250 gigabytes of daily data is just a small subset of all the data that we have. Now, the real problem was that during this time, because of the way we configured Elasticsearch, the nodes that were doing ingestion were the same nodes that were serving the queries. So the queries were all the queries that were sent to the cluster during this time were very slow. So it means that 10 hours a day we had a very unresponsive cluster. The second problem was around querying the cluster in general. So the level of concurrencies that we could get from Elasticsearch was very low, so we couldn't send too many queries in parallel. And again, it is a problem when we are talking about multiple screens that are being used by multiple clients. So this was one problem. And another problem with querying was that because of the way we structured the cluster and how we model the data, each query had to scan all the shards of the corresponding index. So we basically had no partitioning. So each query utilized the entire cluster, which was problematic. So this is a benchmark that we did on our cluster. And as you can see here, even for relatively small number of concurrent queries, 100, the average response time was more than 2 seconds. Again, this is very slow, especially if we are talking about multiple screens using by hundreds of clients in parallel. Each screen in our system can generate tens of queries, so we needed a much higher level of parallelism. Okay, so at this point, we understood that we need to look for a better alternative to Elasticsearch, and we started to investigate the space of count distinct and possible solutions to count distinct in general. And I guess that as probably most of you know, there are a few possible solutions to the count distinct problem. The first solution is just to store everything. So let's say that for our use case, we have attributes, and we want to know the number of unique devices that were assigned to each attribute. We can just store a list to each attribute which contains all the different device IDs that we have seen. And then whenever we want to calculate the number of unique devices, we can just go over this list, do the calculation, and that's it. Now, this solution is not very efficient, especially on the storage aspect, because you need to store all the IDs. We are probably talking about many strings. But also on the time complexity side, because you need to scan the list for each query, it's not very efficient for us. The other option, which is much more efficient, especially on the storage aspect, is to store only 1 bit per device. Now, if you think about it, all we need to know is whether we have seen a device with a specific attribute in a specific day. So we can store a bit vector for each attribute, where each bit represents a device. In our universe, we have 10 billion devices, unique devices. So we need 10 billion bits for each attribute. And then whenever we see an attribute with this device, we can just turn on the relevant bit. And then whenever we want to do the calculation, we just go over the bit vector, check the number of bits that are turned on, and we have the answer. So this approach is, again, much more efficient on the term of storage required. In our case, since we have 10 billion devices, let's say that we have 1 attribute. It means that we need to store only 1 gigabyte per day, which is quite good. But given that we have more than 80,000 attributes, and for each one, again, we need to store 10 billion bits, we will end up with more than 100 terabytes per day, which is quite a lot. And you can understand that for our use case, it's not very scalable. By the way, bit vector is what Elasticsearch is doing behind the scenes. So maybe this can explain why Elasticsearch didn't work for us. Now, luckily, there also exists a third approach, which is to approximate. In this approach, you don't get the exact number of unique devices or unique elements that you have. You get some estimation, which should be close enough. But in return for the loss of accuracy, you get significant improvements, both on the storage required for the solution and on the time complexity. Basically, you get constant storage because you store just a sample of your elements. And the time complexity is also constant because you just need to do few operations in order to estimate the number of unique elements. Okay, so the algorithm that we decided to use is called ThetaSketch. I guess that I'm not sure that most of you heard about ThetaSketch, but I guess that you heard about KMV. But for those of you who don't know, KMV stands for K minimum values, where K is the number, is a predefined constant that defines the number of elements that you store on your sample. And minimum values refers to the process of selecting elements to this sample. So you have an hash function, you operate this hash function on each element that you get, and then you store only the K elements that produce the minimal hash values. With KMV and ThetaSketch, you can estimate set cardinality, which basically means that you can get the number of unique elements or unique devices in our use case. And for us, the biggest benefit was its great support for set theoretic operations. So we could calculate intersection between two sets, union between two sets without losing too much accuracy. And again, this is very important for us since we need to, most of our queries contain some set theoretic operation between the attributes. The only edge case that we found with ThetaSketch was when we tried to calculate the intersection of a very small set with a very big set. Only in this specific case, the error can be pretty high, but Itai will show you later some mitigation tactics. Okay, so just to give you a basic intuition to how KMV works behind the scenes. Let's say that we have people standing in the line. We know the line length. In this case, it's going to be 100 meters. And we want to know how many people we have in the line. So one way of doing that is measuring the distance between each pair and then calculate the average distance. And then if we take 100 divided by the average distance, we will get the exact number of people standing in the line. Very easy. But I want to demonstrate the KMV process. So let's start with K equal to 1. So it means that we will store only one distance, the minimal one. So in this case, the minimal distance is 5. it's also the average distance. So if we will take 100 divided by 5, we will estimate that there are 20 people standing in the line. Now, you can count and see that there are actually 10 people standing in the line, so our estimation is not perfect yet. But let's see if taking a larger k can improve the situation. So now let's try with k equal to 4. So we store the 4k minimal distances. We have 5, 10, 15, and 10. The average distance now is 10. Now if we will take 100 divided by 10, we will estimate that there are 10 people standing in the line. Great. Now, of course, this example is made up, yeah? So don't try this at home. But as you can see here, there is a very strong correlation between the k value and the errors that you can get. And even for relatively small k's, like 32,000, so storing only 32,000 elements from your entire universe, you can get an error which is less than 1% for most of the cases. Also, it makes a lot of sense if you think about it, that taking a larger k value improves the error, because storing more elements, you basically store more elements. So if you store more elements, it improves the estimation. But there is a trade-off here, because if you store more elements, you need to use more storage. So you need to balance between the storage requirements of your solutions and the accuracy requirements of your solution, and find what works best for you. Okay, I will pause here, and now please welcome Itai to the stage.
Can you hear me? Okay, cool. So Yakir talked about the business problem and about ThetaSketch algorithm as a way to mitigate that. But we needed a practical working solution. So after some research, we found about Druid, which is a very fast, highly scalable columnar data store. And in the next slide, we see what that really means. First, I want to give you an idea. So you can see that many companies of all shapes and sizes are using Druid in production, like eBay and the Israeli apps flyer that initially helped us with Druid, Imply, which provides Druid as a service, and many other companies. Now, Druid is very cool, and let's see why. So it can store trillions of events and petabytes of data. It can serve analytic queries in sub-second. It's highly scalable and it's cost-effective. And it also has a decoupled architecture. So, for example, the ingestion process is separated from the query process, which is exactly the problem, as you recall, that we had in Elasticsearch. So the first thing you need to know about Druid is that it's a time series database. So it partitions your data first and foremost by some kind of a timestamp column, like this timestamp column in the example behind me. Other types of columns are dimension columns, which are basically string attributes you can filter your data by, like this attribute column. And the last type of columns are metric columns, where you can aggregate your data by for your analytic queries, like this device ID column. All those types of columns comprise of what is called in Druid data source, which is basically an equivalent to a table in a relational database. The other thing you need to know about Druid is it has a very powerful feature that's called rollup. Now, when we're talking about analytic queries, we don't really care about the raw data, right? We don't care about the raw events in this table in the top part of the screen. But we actually need some kind of aggregated result. So Druid allows you, in ingestion time, to aggregate your data based on whatever you define as part of the ingestion process, and basically get the aggregated, much more compacted result in the bottom of the screen. So then, on query time, you'll need to do something that's kind of similar to a key value store, and only retrieve the relevant response. So, if we take the simple count example, and we're talking about impressions per campaign, let's say we have campaign 111, and we want to know how many devices in general were exposed to this campaign on a specific date. So you can see we have, just count and see, we have 3 impressions for that given date. And this is exactly what will be stored in Druid in order to be queried later during query time. So simple, right? For the count distinct question or answer, as Yakir mentioned, it's a bit more complicated. So using the same raw data that I used, now the question would be how many unique devices were exposed to this campaign. You can see that some devices repeat themselves, and in this example, we want to have 2 as the number of unique devices, not 3, because one of the devices saw an impression for that campaign twice. Now, using an aggregator that is called ThetaSketch aggregator, we can basically get that result of the number of unique devices for that campaign. However, that's not enough for us, because as Yakir mentioned, we want to do things like intersections and unions. So storing the number 2 as the number of unique devices for that campaign won't help us, because, for example, we want to know how many devices were exposed to campaign 111 and campaign 222. And we cannot intersect the number 2 and the number 1, it's meaningless. So in Druid, what we actually store is a ThetaSketch object that contain the sample, as Yakir mentioned. And then, in real time, what we do is, or what Druid does for us, is intersect or unions those ThetaSketch objects in order to give us the query that fulfills the relevant criteria. So in this example, intersecting 2 attributes. Looking at Druid's architecture, it has 3 types of processes. So it has processes to query the data, it has processes to ingest the data, and it has processes to manage all that orchestration. So if we're talking about ingestion, so you can either ingest data in real time through Kafka, for example, into what is called in Druid real-time nodes, or like we do, you can ingest data in batch through, for example, MapReduce jobs into a component that is called in Druid a deep storage. So that deep storage is just a scalable storage like HDFS or S3, and you can see that it's separated from the cluster, from Druid cluster, so we don't affect the queries while we ingest the data. But obviously that's not enough, because even if the data resides in an aggregated format on the deep storage, it still needs to be accessible for queries. So then a second type of nodes, which are called historical nodes, load the aggregated data into disk and memory at the background process, and then it's available for queries. Speaking of queries, a client can send queries to Druid either using the REST API that Druid provides or a SQL interface into a third type of nodes that are called broker nodes. Those nodes basically get the queries, parse them, pass on the relevant parts to either the real-time nodes or the historical nodes that hold the relevant data. And then when they get the partial responses, they do the final aggregation and return the result to the client. Some of you probably identified that this is basically an implementation of the Lambda architecture. If you're talking about how we use Druid in our data flow in production, so we have the raw events that reside on our Kafka cluster. From there, we have Spark applications reading the data and transforming all the raw data into tuples that contain the timestamp, an attribute, the region, which is basically the country in our use case, and the device ID, and that transformed data resides in Parquet files on S3. To aggregate the data and to load it into Druid, we use, as I mentioned, the MapReduce jobs, the built-in MapReduce jobs, using either the sum aggregator for simple counts or the ThetaSketch aggregator, and the aggregated data resides on S3, which is used as our deep storage. And then it is being loaded into the Druid cluster, and that Druid cluster serves queries to our SaaS application, basically to the screens that Yakir showed you earlier. As part of the POC, and you remember one of the first slides, we've done a benchmark with Elasticsearch and with Druid. So with Elasticsearch, the average response time grew exponentially as the number of concurrent queries grew, which obviously wasn't good for us, and it didn't really matter how large we made the Elasticsearch cluster. However, with Druid, you can see that even with several concurrent queries, the average response time was somewhat linear, so we can scale out our Druid cluster as our number of concurrent queries increased and still get very good performance, even though we had thousands of concurrent queries. So we've seen what is Druid. we've described the architecture and how we use it in production. And now for the, I think, really interesting part is we want to share with you some of the guidelines and pitfalls we've learned over the years of using Druid. So for us, setup wasn't easy, and it took us a few months to get to an actual production deployment. Luckily, there are several things you can use. So you can use Druid online documentation in order to set up your cluster. And also, Druid UX has improved significantly in the recent versions. So we're hoping, and the community, open source community, is aiming to make your Druid setup much easier. We also wanted to provide an actual example from one of our Druid clusters. So we have several Druid clusters in production, and this is just one of them. So I mentioned we're using S3 as our deep storage. We have about 10 data sources or tables in that cluster. All of them are using ThetaSketch. The size of the aggregated data on that cluster is only 40 terabytes, even though we're ingesting dozens of terabytes per day and we need to hold 1 year worth of data. So, as I mentioned earlier, as part of the rollup process, we get a much more aggregated, compacted results, and this is the reason why we only have 40 terabytes on that cluster. For broker nodes, and for those of you who are familiar with AWS, we're using R48XL instances. If not, that's fine. Those are basically instances with 32 cores and 244 gigabytes of RAM, and we have 3 of those. As per the historical nodes that hold the historical data, so we have 17 i38XL. The spec is kind of the same, but in this case, we have very fast SSDs that are called NVMe SSDs, and I'll discuss it in the next slide. So another thing you should do with Druid, as with any other system that you're using, you should really monitor it. And luckily for us, Druid is very verbose and it can emit a lot of metrics. We're using Druid's built-in Graphite integration in order to send those metrics into an hosted Graphite service and build Grafana dashboards on top of that. Again, giving you an actual example from one of our production clusters a couple of years ago, you can see that in some point in time, we had a significant spike in the query time, on the average query time. We're talking about over 10 seconds, which is obviously very bad for real-time analytics. And we started looking into what we've seen, or what metrics were provided for us by Druid. And one of the metrics popped out, that is called pending segments, and I'll describe it in a second. But you can see there's a correlation here between the number of, or the amount of pending segments and the average response time that spiked as well. We're talking about almost 10,000 pending segments. And pending segments is basically a term that means that Druid had to load all that segments or aggregated file parts to memory in order to serve the queries. Now, once we've switched to, remember those very fast SSDs, we were able to significantly reduce the average response time because loading those files into memory was much faster. So dealing with databases, data modeling is very important, obviously, and we will provide 2 examples here. The first one will be reducing the number of intersections, and Yakir mentioned the edge case with ThetaSketch, where if you want to intersect a very large set, so for example, well, all the devices in the US, and a relatively small set, for example, all those are interested in Porsche, so you might get a very high error rate. For us, the original data model was a timestamp column with the date, an attribute column, and everything was an attribute. So the region was an attribute, or the country, Porsche intent, everything was an attribute. In order to answer the question how many unique devices in the US were interested in Porsche, we had to intersect those 2 ThetaSketch objects and get a very high error rate. To mitigate that, what we've done is to extract the region into a new dimension. And now to answer the question how many devices in the US are interested in Porsche, all you need to do is take the specific single ThetaSketch object and extrapolate the number of unique devices, so there are no intersections. That obviously doesn't fulfill, or answer all edge cases, but it gives you an idea of how you can mitigate such problems. Another thing you can do is have different data sources for different use cases. So for example, if you need very fast queries, and you can tolerate a penalty on query accuracy, you can have a data source with a relatively small k, right? A relatively small number of samples, so for example, 4,000. So your queries will be very fast, however, maybe not as accurate. On the other end, if you need very accurate queries, and you can tolerate a bit of a penalty on the query performance, you can have another data source with a relatively high k, for example, 65,000, and you'll get very accurate results, and maybe your queries will be a bit slower. So query optimization, as I've shown you earlier, was very important for us because we're talking about real-time analytics. A few things we found out. So the first one, I mentioned that Druid has a REST API. You can send queries over and get the answers. Now, we've discovered that combining multiple queries on top of one single query or one single REST API call managed to reduce the average response time. About filters, so if you're using the REST API, we really urge you to use filters as early as possible as part of your query in order to gain those speed optimizations you can gain using filters. And the last thing I want to talk about is, again, using those NVMe SSDs, which also helps you to speed up the queries as part of loading the data into memory when it needs to serve the queries. And there are many other things you can do, and the slides will be up there later, so you can learn from that as well. So we mentioned that Druid is also cost-effective, and I would like to spend a minute about doing cost optimization for the batch ingestion process that I mentioned we're doing. So we're using Elastic MapReduce in order to spin up MapReduce clusters on top of AWS and ingest our data in batch. We had a fairly large cluster, 140 nodes cluster, and once we switched 85% of those instances to be spot instances, which is kind of equivalent to Google Cloud's preemptive VMs, we're able to reduce the cost by 80%, which is significant in any use case out there. When we started with Druid, we used the simplest format, CSV, as for POC purposes, but switching to the columnar format of Parquet, we're able to reduce the ingestion time by a factor of 4, and the Druid, the used storage by a factor of 10. So another great benefit you can, another thing you can do to benefit from that ingestion process. And the last part, as for the ingestion process, was I mentioned that we have a Spark application reading data from Kafka, and later on writing it to S3 before it's being aggregated into Druid. So my colleague had a really brilliant idea of pre-aggregating the data as part of the Spark application, because we already had the data in there. So aggregating the data, either using Spark's group by action for simple counts or combined by key for distinct count, and also increasing the length of the microbatch from 30 minutes to 1 hour to get a better aggregation ratio. We're talking about a factor of 2,000 in terms of how many output records we had before that optimization and after. And in total, we were able to save over $2 million yearly for that optimization alone. So dealing with open source, obviously, thanks. So dealing with open source is, it's very important to have a vibrant community. So luckily for us, Druid has a very helpful community, and we encourage you to use the Google groups and the GitHub repository in order to ask questions and help others. And we have many things we plan to do. So for example, we're currently researching for machine learning tools that will help us improve the accuracy of small set and large set intersections that I mentioned, version upgrades, and stuff like that. So to summarize what we've learned that answering count distinct questions in real time is a challenge, and luckily for us, approximation algorithms are for the win here. We've learned that Druid provides you a concrete implementation of the ThetaSketch framework, and the Druid is a time series database. It can store trillions of events and serve analytic queries in sub-second. It's very scalable, cost-effective, and used widely among big data companies, and can be used for the distinct count and the simple count questions. We've learned that setup isn't easy, but luckily you can use various online resources as well as the recent developments in the UX in Druid in order to get to a production deployment. We've seen that ingestion has very little effect on query performance using that deep storage component. We also seen how Druid provides you good visibility into what's going on in your cluster, and now you can use it in order to mitigate production issues. And lastly, we've seen that if you carefully design your data model and build your queries, you can significantly improve your query performance. Just before I wrap things up, two things we care about. So Women in Big Data is a worldwide program that aims to inspire, connect, grow, and champion the success of women in the big data analytics field. And there are over 20 chapters and over 14,000 members worldwide. We actually launched the Israeli chapter about 6 months ago. And everyone can join regardless of gender. So we really encourage you to find the chapter near you using that link. Also, we have an active tech blog where we try to write about the interesting things we do around the Nielsen Marketing Cloud. And a recent post we published, and I think will interest you, is about deleting data and retaining data in Apache Druid. That's it for us, and we'll be taking questions now. Thank you.